line integral of second kind. Let us have some part of space G, and we have some vector function a, which equals p of x, y, z I plus q x, y, z g plus r x, y, z k be defined, where p, q, r are scalar functions that are defined inside this space also. So if we have this vector function defined, we can tell that inside this space G we have a vector field A defined. It can be anything like field of velocities of moving liquids, or electrical current, or some forces. So let us have some force F Pi plus Q plus R K, where P, Q, R are some continuous in G functions. Let us assume that we have some line and an epimetrial point moving along this line, and when this point is moving, some force F conducts some work A. And to find this work, we have to split this L into several pieces, Li. And these pieces will be defined by points A, 0, A1, A2, and so on till AN. First point will tell it's equal A, final point equal B. And these pieces will denote as delta Ri. So this will be vector from ai minus 1 to ai. At each element Li we'll select mi, and we'll presume that force F will be constant on every piece delta Ri F of mi. Then work of force F to move point from ai minus 1 to ai will be delta ai approximately vector F of mi multiplied by delta Ri scalar. This is scalar multiplication. So if we try to approximate total work, this will be sum I from 1 to n F of mi delta Ri, and if we will minimize delta Ri and maximize number of pieces, we will get exact expression for this work. This will limit maximum delta Ri absolute value tends to 0 and tends to infinity, sum I from 1 to n F of mi delta Ri scalar multiplication. We can have not only force but also just some average field. So let us have these functions p, q, r continuous at every point of some smooth curve L, and L will be defined as x of t, y of t, z of t. So we will have to define starting point A, x of alpha, y of alpha, z of alpha, and endpoint B, x of beta, y of beta, z of beta, where alpha beta are endpoints for t. If we select this curve and say that we have some way, some direction of passing this line, then we have oriented curve. So if we write down that we have L plus, that means that L is oriented from A to B. If we write down L minus, then L is oriented from B to A. We can change this orientation choosing direction of tangle vector. Let us now consider function A, vector function that consists of pi plus qg plus rk, or the functions that can be just written as a of x, y, z. If we make same operation, split this curve into pieces as in previous problem, then we'll get same approximation. We will get sum I from 1 to n, scalar product A of xi, yi, zi by delta ri, where xi, yi, zi are coordinates of point mi. So, if we make this delta ri very small and number of pieces very large, infinite, we will get our line integral definition. So integral by line L of function A by differential of r is limit maximum delta r I tends to 0 and tends to infinity of sum I from 1 to n A of mi by delta ri scalar multiplication. If we have dr as dx, dy, dz, then this integral can be rewritten as integral by L p dx plus q dy plus r dz. If we have parametric representation x of t, y of t, z of t, then, as we remember, differential of curve L is square root of x prime square plus y prime square plus z prime square dt, which we will denote as absolute value of some vector tau dt. This tau is a vector that is tangled to curve L at point M, x of t, y of t, z of t. If we write down t0 vector, which will be vector t over vector tau absolute value. So what will we do here? We obtain same vector as tau, but we make it a vector of length 1. Then this expression can be rewritten: p dx plus q dy plus r dz will be px prime dt plus q y prime dt plus r z prime dt, and we can just integrate it as one function by t, but same expression can be rewritten as scalar product of a and tau dt, or a tau 0 dt. Properties of line integral of second kind. First one is linearity. If we have some two functions and we have two numbers, alpha, beta, average, then this integral can be rewritten as integral by L a1 dr plus beta integral by L a2 dr. If we have, this is our first property. Second property, if we split curve L into two pieces, L1 and L2, then integral by L a dr can be calculated as integral by L1 a dr plus integral by L2 a dr. Third property is if we change orientation of our curve, we'll have different sign. So if we go from A to B, we'll get. If we go from A to B, we get plus. If we go from A to B, we get plus. If we go from A to B, we get plus. If we go from B to A, we get minus. But how to calculate this integral? First case we will consider where x is x of t, y is y of t, z is z of t. Parametric curve. Here our integral of p dx plus q dy plus z, r dz by L will be transformed to integral from alpha to beta if t is from alpha to beta. P of x of t, y of t, z of t, x prime dt plus same for q of x of t, y of t, z of t, y prime dt plus r of x of t, y of t, z of t, z prime dt. So we just substitute everything with t and calculate this integral. Second approach, if we have two-dimensional curve, which is also specified in parametric way, we will get pretty much the same. Integral by Lp dx plus q dy will transform to integral from alpha to beta. P of x of t, y of t, x prime dt plus q x of t, y of t, y prime dt. if we have a curve that's specified by equation y equals f of x is from A to B, then we can transform integral by Lp dx plus q dy into next form, integral from A to B, p of x ef of x plus q x y of x y prime dx.